First of all, I would like to thank the organizers for organizing such a nice online event and giving me as well as other participants the opportunity to present their own research. So hi, welcome to my talk. I'm Sayan. I'm a third year PhD student at Columbia University. My advisor is Ivan Corwin. So today I'll be talking about upper tail large deviation of the KPZ equation, and this is a joint work with Leicheng Tsai. So let me first describe what the model is. So the Kardar-Persisang equation, or the KPZ equation, is a universal model for random growing surfaces, HDX, that satisfy this stochastic partial differential equation. Here, zeta is the space-time white noise. So this equation makes sense formally. However, mathematically, this equation is ill-posed because of the presence of this nonlinearity term. So in order to make sense of this equation, one needs to do some other things. So people, what they usually do is they consider stochastic heat equation with multiplicative noise, which is given by this equation too. This equation is well posed. One can solve this equation. And if you take the logarithm of this solution, you get back the KPZ equation formally. So in that sense, if you define htx to be the logarithm of ztx, then this is known as the Hopkohl solution of the KPZ equation. Okay. So in this talk, I'll be considering Dirac initial data, where that is z of 0x would be delta of x, where delta is the Dirac delta function, and I will be considering the Hopkohl solution of this initial data. Well, if you consider this kind of initial data, it turns out like z is always non-strictly positive, hence logarithmic makes sense. Hence, the solution hdx is actually well defined. So let me first talk about the large time behavior of hdx. So we have spatial stationarity. If you look at the distribution of hdx and add a parabola to it, then it is same as the distribution of ht0. So for a given time t, the height essentially looks like an inverted parabola roughly. If you are interested in the distribution of hdx, it is enough to talk about the distribution of ht0. So Amir, Corwin, and Questel in 2011, they were able to give an explicit expression of this distribution of ht0. And they also provided Tracy-Widom fluctuations. Essentially, if you consider h2t, 0 plus t over 12 and divide it over t to the power 1/3, then this expression converges to the GeV Tracy-Widom distribution. Well, for technical reasons, we consider h2t, 0. You can consider t, 0 as well. It doesn't matter. So after proving this result, a natural question arises: what happens to the tail of this quantity h2t, 0 plus t over 12? So as the title of my talk suggests, I'll be considering the tails of the KPZ equation. So in past decade or so, there has been a tremendous progress in understanding the tails of the KPZ equation, but because of the lack of time, I cannot give you an overview of the literature. So in this talk, I'll be focusing only on the large deviation regime. So I'll be talking about what is the probability that h2t, 0 plus t over 12 has deviations of order t. So we can have two kinds of deviation. It can be deviations on the lower side. That means h2t, 0 plus t over 12 is less than equals to minus ty, which corresponds to the lower tail, or h2t, 0 plus t over 12 is bigger than equals to ty, which corresponds to the upper tail. So it turns out for the lower tail, the probability has a decay of e to the power minus t squared times the function, while for the upper tail, the probability has a decay of e to the power minus t times another function. So the two tails actually have different speeds. So these are all approximate. So in 2018, Leicheng Tsai was able to prove the lower tail large deviation principle for the KPZ equation. He essentially shows that the probability when you take the logarithm and divide it by 1 over t square, then this limit exists, and it is given by some function phi minus. This phi minus function is very explicit. It's a polynomial kind of function, but I haven't written out in the slides. So in this talk, I'll be considering our result about the upper tail large deviation of the KPZ equation. So last year with Li Cheng, we were able to prove that for any y in this range, the probability that our quantity is bigger than ty, if you take the logarithm and divide it by 1 over t, then the limit exists, and this is given by this function. So essentially, the large deviation rate function is given by this function minus 4/3 y to the power 3 over 2. Okay. So let us briefly go through the proof idea. So one of the standard way to prove upper tail large deviation is to get a good control of all the exponential moments. Once you have a good control of it, you can use the Markov inequality and exponential tilting to get a good idea about the upper tail large deviation of your random variable of interest. We use the same idea in our setting as well. So since KPZ equation is an integrable model, thanks to the integrability, we have a couple of exact formulas. We do know something about the exponential moments when n is a positive integer. It is given by an n-fold integral. And we do know about something about the Laplace transform of this random variable, and it is given by a freedom determinant. So the first formula is valid only when n is a positive integer, and it is not enough to get a good control of all the exponential moments, and it is not, and hence it is not enough to get a good idea about what is the rate function is actually is. So we actually use the second formula for the Laplace transform, and we use it to get a good idea about all the exponential moments. So we essentially use this elementary lemma. So what this lemma is telling about, like if you have a non-negative random variable u, and if you fix n and alpha in this region, and if you want to consider what is the fractional moment of this quantity u, you can actually get an idea about this guy by using this formula. So note that we have a Laplace transform of u. If you take the derivative, hit it with s to the power minus alpha and integrate it out, and then normalize it appropriately, you will get an idea about the fractional moments. So using this formula, this elementary lemma, and this freedom determinant formula, we were able to deduce some kind of formula for the fractional moments. Once you have a good, and this will give you a good control about the fractional moments. So using this idea and by a bit of analysis, we were able to show for every p bigger than 0, the exponential moments looks like e power p cubed t over 12 as t tends to infinity. Using this idea as well as the idea that I described before, this Markov and tilting, we were able to deduce that the upper tail large deviation is actually minus 4/3 y to the power 3 over 2. The reason we get this function is because the Legend differential transformation of this pq over 12 is exactly minus 4/3 y to the power 3 over 2. So that's the end of my talk. Thank you for your attention.